Let's just dive right into this explainer, shall we? Today, we're unpacking the science behind mountain avalanches. We're talking about these fascinating, ridiculously powerful, and often completely hidden frozen realities. And, as you'll see, our changing world is quite literally rewriting the rules of the mountain. Seriously? Think about it. When you look up at a breathtaking, pristine, snow-capped peak, what's actually hiding beneath all that beauty? It looks perfectly peaceful, right? But underneath that surface, there's a highly volatile physical process constantly at play, just waiting for the exact right moment to release.
It essentially boils down to the ultimate tug-of-war of mountain physics: gravity versus friction. At its absolute core, an avalanche is simply a rapid flow of snow down a slope. But it's driven by this constant, invisible battle. You've got gravity desperately trying to pull all that massive weight down, and the friction of the snowpack desperately trying to hold it safely back.
Here is our roadmap for today. We're going to cover the physics of avalanches, the anatomy of the snowpack, the Cornice hazard, climate change and snow, and finally, the wet snow shift. Let's get into it.
Part 1. The physics of avalanches. So avalanches don't just happen anywhere. They overwhelmingly occur in what experts call the danger zone. We're talking slope angles between 30 and 45 degrees. It's kind of like a Goldilocks situation for disaster. If a slope is too flat, well, friction wins out. If it's too steep, the snow just sloughs off before it can even build up into a dangerous mass. But right in that 30 to 45 degree sweet spot, that's where a massive, cohesive slab can form, and gravity almost always wins.
And whether it's triggered by falling ice, heavy wind, or just a human skiing across the slope, the sequence of a slab avalanche is remarkably exact and deadly. Step 1. A buried weak layer in the snow collapses under the weight. Step 2. A massive fracture. We call this the crown. Instantly shatters right at the top of the snowpack. And step 3. That entire massive slab slides down the firm layer beneath it, the bed surface. This thing can move at literal hurricane-force speeds, generating an unbelievable amount of kinetic energy. Moving on to part 2, the anatomy of the snowpack. If we zoom in over the course of a winter season, every single storm, wind event, and sunny day leaves a very distinct signature in the snow. Sometimes, cold, clear weather causes snow crystals to morph into loose, unconsolidated grains. They honestly look a lot like sugar. Now, if a heavy slab of brand new snow falls on top of those sugary grains, well, you've just built a trap. In fact, avalanche experts specifically refer to these highly porous layers as the mechanical flaw responsible for slab avalanche failures. Think of it like a collapsing house of cards. Without that weak layer acting as the failure point, the massive slab above it wouldn't have the slick runway it needs to actually slide. Identifying these hidden flaws is quite literally a matter of life and death. Part 3. The Cornice hazard. Let's zoom back out to the terrain. We absolutely have to talk about cornices. These overhanging masses of wind-deposited snow are incredibly deceptive and destructive. They form on leeward ridges, that's the side protected from the wind, and they can grow to be the size of a school bus. What makes them completely terrifying is that they release suddenly, often during rapid temperature warm-ups, or even just by someone standing nearby. And they can break far back onto what looks like a totally flat ridge, potentially sweeping victims right over cliffs. Plus, the sheer impact of all that falling ice, it can trigger a massive slab avalanche on the slope directly below. So the golden rule here is beware the obscurate horizon line, because without a visible gaping crack, you might be standing on a massive overhang without even realizing it. This applies to anyone out exploring winter terrain. Always, always give unknown edges a wide berth. Cornices break much further into a ridge crust than you'd ever expect. Part 4. Climate change and snow. Now we have to pivot to a really fascinating question. How is a warming world fundamentally altering the avalanche mechanics we just talked about? According to some advanced simulations run on the Swiss Alps, we are looking at a potential net reduction in total avalanche activity of up to 60% at lower elevations by the end of the century, assuming extreme emissions. Scientists use sophisticated snow cover models to project the mountains of the year 2100, and the findings are pretty staggering. Now, you might be thinking, well, warmer air means less snow and fewer avalanches, right? It seems totally logical. But high elevation zones are actually facing a highly dangerous and completely counterintuitive surge. Sure, the total volume of avalanches might decrease as the snowline gets pushed higher and higher up the mountain. But the fundamental type of avalanche happening up high, it's undergoing a massive transformation. Which brings us to part 5, the wet snow shift.
To understand this surge, we really need to compare two entirely different ways that snow can fail. On one hand, you have dry snow avalanches. These are the ones failing on those cold, sugary weak layers we talked about earlier. On the other hand, we have wet snow avalanches. These fail because liquid water, either from rain or spring melt, infiltrates the snowpack and absolutely destroys the bonds holding the snow together. Warmer temperatures are actually stopping those cold, persistent weak layers from forming, but they are massively increasing that liquid water infiltration.
The data illustrates a wild, diverging future. While dry snow avalanches are projected to plummet across all elevations because it's simply getting too warm to form those fragile, icy layers, wet snow avalanches at higher elevations will actually see a drastic 10 to 30% spike. So we are quite literally trading one type of natural hazard for another.
And, it's not just the type of avalanche changing. It's the timing, too. Wet snow avalanches have traditionally been a spring hazard, tied to the end of season melt. But going forward, they're going to start happening right in the middle of winter. The infiltration of liquid water is shifting earlier and earlier, creeping right into December, January, and February. So what's the big takeaway here? The vital paradigm shift is this. Less snow doesn't mean less danger. It just means a different, wetter, out-of-season danger. Models are projecting up to a 3-fold increase in winter rain on snow events. And that means we're going to see powdery dry slabs replaced with heavy, wet concrete sweeping down the mountainside when people least expect it.
Which leaves us with a really pressing question to ponder. Are our current safety protocols, our mountain hazard maps, and our backcountry habits actually ready for an entirely new, wetter, and warmer era of avalanches? The snow beneath our boots is rapidly transforming, and it's pretty clear our respect for it has to evolve just as fast.